Hi, everyone. So for our first paper in this session, we have Decrypting Distributed Ledger Design, Taxonomy, Classification, and Blockchain Community Evaluation by Mark Ballandies, Marcus Dapp, and Evangelos Pournaras.
Well, a bit scattered. Can you hear us?
Yes, you're on.
Okay, great. So we just go ahead?
Go for it.
Excellent. So good morning, everyone. Thanks, Wasim. Thanks, Dan, for having us virtually only, but well, we would love to be there with you right now, but we're happy we are able to present nevertheless. My name is Marcus Dapp. I'm a senior researcher at ETH, and Mark, our co-author, we're presenting the paper, and I will just have the first few slides giving a bit of context to the whole thing. So actually, we are in a project that's called Future ICT 2, and in which we are working on a new socio-ecological monetary system, which we call Finance 4, which is based on blockchain technology. And as you can imagine, several questions came up during that project over the last 3 years. And one of them was research into multidimensional incentive systems. And 2 years ago, there was not much around in analyzing and synthesizing how DLT systems actually work. So as sort of a side project out of the main Finance 4 project came the idea of working on a taxonomy. And that's exactly what we want to present today, as you can see on the chart in the left bottom corner. But if you're interested in the Finance 4 project as well, I will show a few slides and links at the end of the presentation. So what was the motivation? Well, we realized that this design space for a techno-socio-economic system is really vast and complex. And although many people would agree that a lot of altcoins are sort of copycats from other existing coins, there's still quite a lot of space to cover. A few examples on the right side, what you can think of when you design such a system. Could be permissionless. We have several proof of X mechanisms for consensus, fungibility, Turing completeness of smart contracts or not, anonymity questions, fees, how the tokens are handled over the long time, etc., etc. So there's a lot of stuff. And at that point, we didn't find a structured way of analyzing how these many projects actually differ. And so we came up with 2 research questions out of the larger project, which were the first one being an analytical one. So how to systematically and quantitatively derive, compare, and evaluate design choices in DLT systems. So what makes Bitcoin and Ethereum differ from Ripple or Dash or Monero? And then in the course of this analysis and doing additional quantitative analysis, we also cover a second research question with which we hope to help people to design such systems, not only analyze existing ones, but design their own. So what are key generative design choices in DLT systems? How did we approach this? The methodology is, as you can see, more or less 4 larger steps. We started with a conceptual architecture, which Mark will show you in just a few minutes, in which we try to describe analytically how we think DLT systems can be described in a systematic way. From that, we use Nickerson's taxonomy methodology to actually come up with a taxonomy, which is a more rigid, a more strict way or formal way, let's say, of presenting this design space. After having created this taxonomy, obviously we had to check whether it actually works. So we took, for the current paper that you can read, we classified around 50 existing DLT systems by ourselves and other people around us. And in a second step, asked the communities of these projects to verify both things. As you can see in the dotted box in the middle, we asked them for feedback about the taxonomy itself. Does it make sense? Are the right questions asked? And also to give feedback on how we classified their project. After having that, we created a nice table, a nice database, and we were able to run some machine learning, mainly cluster algorithms on it, to basically reduce the complexity of the space and switch from a more analytical to a synthesis approach, helping projects and other researchers in exploring this space, particularly in the areas where not much is done, neither in academia nor with practitioners at the moment. So, and Mark will now go through all the 4 components, and we will see each other at the end of the presentation. Thanks.
Yeah, hello together. Also, hello from my side. Would have loved to be with you now in Boston. Okay, cool. So we ask ourselves, what are the key generative design choices in these DLT systems? And I will walk you now through our methodology and show you a bit in greater detail what we did in each of these components and what we found. So let's start with the conceptual architecture. Before illustrating the architecture, this is how we see DLT systems. So we have a distributed ledger in the system. We have some actors here on the left, which perform actions in these systems. These actions get digitally represented and written to the distributed ledger via a consensus network. And this maps to our conceptual architecture, which consists of 4 components. So we have an action component, a consensus component, a distributed ledger component, and additionally a token component. And all of these components, they are interacting with each other. So actors in the real world, they can perform actions. These actions are digitally represented as a claim. The writers of the consensus network take these claims, they write them as a transaction to the distributed ledger. And in some systems, actually this writing triggers the creation of new token units, which are rewarded to the writers of the system. And the writers, they actually perform this work because these tokens have value. And the source of value we call underlying. So for example, this underlying could be computational power in the system on the distributed ledger, could be maybe a voting right in the consensus, could be another token, or maybe goods and commodities. And as an example, a well-known network we all know, Ethereum. So actors can write smart contracts in this case. These smart contracts are sent to the writers who writes them to the distributed ledger. And these writing to the distributed ledger triggers the creation of new Ether tokens, which actually have value because the actors, in order to access their smart contracts again, they need these Ether tokens. Basically gives them access to this computational power of the network. Okay, and what we're doing in our Fin4 research now is more looking what actually happens if not just the consensus actions triggers the creation of new token units, but what actually happens if, for example, the planting of a tree also ends up in the creation of new token units. Okay, so now coming from this conceptual architecture, we used the method introduced by Nickerson to derive a taxonomy. The taxonomy looks as follows. So we have again our 4 components in orange boxes: the distributed ledger, the token, the consensus, and the action. But now each of these components are described in greater details by attributes. And these attributes, they can take several values, characteristics. And for example, the distributed ledger can be of a specific type, for example, blockchain or a directed acyclic graph, or the consensus, the write permissions, so actually who can write to the distributed ledger. It could be public or restricted, just to illustrate some of them. And these 2 components, the distributed ledger and the consensus, actually, they make up this distributed ledger technology. But we also have the cryptoeconomic design part on the right. And in the end, if we want to incentivize actors to perform specific actions, these tokens, they need to be designed in a way that they are wanted. And the taxonomy can support, like in analyzing these tokens in greater detail. So just an example of how this taxonomy could be used is that now we have this token component, and we have in these 6 attributes which describe this token. For example, the supply. So a token could be capped or uncapped. It could be burned. The creation of new tokens, it can be conditioned. So maybe it's connected to the consensus. Okay, so I get some noise in my audio. Okay. Yeah, so that's like how the Monero token could be mapped, and that's like how Ripple is mapped. And now this utilizing this morphological box, I can support you. Okay. Okay. So we compared our taxonomy with related work. We noticed that basically most taxonomies we found they don't consider token properties in the taxonomy. Also, just some of them used actually taxonomy to classify real-world systems, which could be seen as a missed opportunity to validate the taxonomy. And none of the works we found actually performed the validation of the taxonomy by the community, or like kind of a third source to validate it. And also the works usually didn't utilize a quantitative analysis, which we show can be used to actually derive such design choices in a more objective way. Okay. So now we have this taxonomy, and we classified it. And so we observed what is out there. And in order to be here more transparent, we designed a system identification process. So we sourced our systems from two well-known sites. One is CoinMarketCap, the other one CoinCodeCap. We merged the data we found on these websites. We enriched it with basically with the criterion if these systems have been mentioned in academic literature, because we wanted to kind of as an importance measure of these systems. Then we ranked them based on this ranking function, where we considered the market capitalization of a system also as a proxy for its importance, but also the community contribution to the system. So how many commits are there, where they are like in the last year, I think, and how many actors actually contribute to the source code. So mapping the viability of these systems. And from this ranking, we chose the top 50 systems, which we classified. And here, like as an illustrative example, we show how these 50 systems look for the distributed ledger component. Okay. So now we have this taxonomy and classification. And we wanted to evaluate it. So we used the user study and the wisdom of the crowd, basically, to give us some feedback and to inform us. And these were the demographics of the people we reached out with our questionnaire. So we had 85 people responding with a completion rate of 58%, which in the end we used also for the analysis we performed. All in all, one could say that we have had a pretty experienced participants field. Like we had like 29 people who were already in the field from 1 to 3 years, which gave us some confidence about the results. The questions asked to the participants. So the survey was divided in two parts. So in the first part, participants were asked about their system. So so if someone contributed to Bitcoin code or was mentioned on, for example, the Ripple website, we sent them our survey with their system classified, and they could basically agree, disagree with our classification. And in this process, they also learned about the taxonomy. And in the second step, they had to evaluate how expressive actually the taxonomy is to differentiate between and classify all DLT systems. And this expressiveness criteria was constructed based on the comprehensiveness and robustness criterion as defined in the paper of Nickerson. So the main motivation is actually, can we use the taxonomy to classify all the systems which are out there? And this is also useful to differentiate between these systems. And on average, we obtained an 84% acceptance rate for the classification. And for the taxonomy, on average, 79% of expressiveness. Yeah. Okay, so now we are having these. We had this. Now what we have is basically a taxonomy from which we think, or like also validated, that it's expressive enough to describe systems out there, and we have a data source which is validated by the community, and we applied now some machine learning on top of it to derive these design choices. Yes, because like just to remember that these systems which we classified are actually those which are uh, important one, so to say, and viable in the system. So they are still there. They have a market value. So basically, wanted to learn on these kind of systems. And why are we doing this? As a remembrance, just our taxonomy, which we have here, it already, which is by far not exhaustive, allows for, I think, over 3 million different types of configurations, so different system layouts. And as one can see, the complexity of the configuration space is large, and we wanted to, limit it a bit. So we applied two methods on top of the data. The one is k-means, which is pretty popular in data mining. It partitions the data into clusters, and the number of clusters you will see later, we bootstrapped them. And the second method we're utilizing is the multiple correspondence analysis, which is more used in the social sciences. It's a generalization of the principal component analysis for categorical data. And the nice feature is that one does not have so many priori assumptions as in the k-means. So one, for example, does not have to specify these clusters. And what multiple correspondence analysis actually does is that it identifies new latent dimensions, which are, in our case, a combination of these attribute values. So it's kind of, maybe see some patterns, could identify some patterns in the data not seen before. And here are the results when applying MCA on the data. We identified that the first 4 dimensions are actually significant to explain over 95% of the variance in the data. We named these dimensions. So the first dimension we described as layering, the second as participation, the third as staking capability, and the fourth as cryptoeconomic complexity. And how did we arrive to these namings? We created such Sankey plots, but we reinterpreted them a bit, or reused them a bit. So what we see here is the squared cosines of each of these attribute values. So basically the contribution of each attribute value to the construction of the dimension. So here we have like permissioned participation, and we see that usually systems which have a permissioned participation, they don't use consensus fees. They have a different type of proof type. So they don't use a proof of work or proof of stake. The write permission is usually restricted. Actor permission is restricted. So that's the flow from the left to the right. And from the right to the middle, we see how much the systems actually contributed to the construction of this dimension. In this case, biggest contributor was the Ripple for this dimension. Okay, then applying k-means, we identify 3 clusters as the most stable clustering. And now plotting these 3 clusters in the 2 dimensions which we identified before with MCA and labeling them based on the clusters from k-means, we see that both methods more or less find the same clusters, which can be described as second layer systems. An example is Aragon. So systems which are utilizing another distributed ledger technology system as infrastructure. We have permission systems like Ripple, and we have permissionless systems like Bitcoin. And now in the final step, we utilize these findings to construct a design guideline. And in this design guideline, we ask 4 questions, which are ordered by importance based on the MCA analysis. So which can guide now researchers and practitioners to design a new system. So the first questions one, for example, has to address is, do you want to use a first layer system or a second layer system? And then what should be the participation level in your system? Do you have some staking? And what is the general cryptoeconomic complexity? And and what we provide is for each option, which one chooses, a default attribute value configuration, and also example systems, which more or less align with these choices. And the significance of this approach is that this whole guideline is derived quantitatively from this validated empirical data. Okay, so let me conclude. We think that our contributions support researchers and practitioners to analyze and design DLT systems. In particular, the conceptual architecture and taxonomy, they map the design space and they stress the difference between similar systems. The classification informs about existing systems and can also inspire like how the systems look like. And the design choices in the end limits the modeling complexity at design time. And the overall contribution is this methodology, which can now be reused to further identify design choices. For example, one could extend the classification and reapply the same methods or another machine learning methods. One could extend the taxonomy. So we found in our user studies that the token component, the action component could need some more attributes to be even more expressive. And we also found that, for example, the conceptual architecture, it could be extended with the governance component, and all of these steps would need to would lead to a reiteration of these steps, but potentially in the identification of more choices. And I give for the last minute over to Markus. So thanks a lot.
So Markus doing the hard work. Thank you. So I want to extend a second invitation, actually. The first would be have a look at the paper. It's on arXiv in version 2. We are very happy to receive all and any kind of feedback you may have. And we are also, well, we realize it's quite abstract and a lot of conceptual thinking needed to go through such a taxonomy. So we are in the midst of creating a website, which we call Bloxonomy, but at the moment you can only see it on an IP address, which is shown on the slide right now. Have a look there. We have all the 50 systems and their classifications online. You can click through. We have some first, I think, nice graphs there as well, I'd say. And there's also a possibility to give feedback to the classifications, and we want to extend that in the future so that people and communities can also enter their own projects there. So ideally, this develops in some sort of community resource on well, DLT systems and how they function. The last slide, the left side is some further work. If you're interested, it's also mentioned in the paper itself. On the right side, just to close the loop back to the Finance 4 system, again, here we try to motivate sustainable behavior and empowering communities to issue tokens to incentivize sustainable behavior, which we call Finance 4. We have a running software prototype running on the Rinkeby testnet of Ethereum, if you want to have a look at the demo. There will be an ebook published in a few weeks, hopefully. The website is there. And again, the IP address of Bloxonomy and a few multimedia stuff on YouTube. So thanks a lot. And I hand over back to Mark. And if you still have time for a few questions, happy to hear them. Thanks.
Thank you. Can you hear us all? Can you hear us all right now?
Yes.
Okay, great. All right, so if anyone wants to ask questions, you can line up at the mics here. And I think our first question is from Wasim.
Hi, Marcus and Mark. Thanks very much for the talk. So I may be the only person in the room that's actually read the Nickerson paper, because I built a taxonomy framework using Nickerson's paper as the basis on a project called Token Space. So one of the key things in the Nickerson methodology is to select an overarching meta characteristic. And I don't think you necessarily called it by that name. So I'm just wondering what your design choices in the initial stages of building your taxonomy following the Nickerson methodology were, specifically with the a reference to this overarching meta characteristic concept.
Yeah, so it's quite some time until when we performed these steps. So what we did is, so we started from these two, like what Nickerson does is like starting from this conceptual view and also like observing systems in the real world. And so we started from this conceptual architecture, which we described there. And these meta characteristics are our components in the end as we see them. Yeah, so we started from this conceptual architecture, then looked out what could be characteristics or like attributes describing these components, and then we checked like real-world systems if actually we can like classify them based on these attributes, or if we need to extend them with further attributes. Yeah.
It's interesting. I think we actually used the Nickerson methodology in slightly different ways. So I'd be very happy to send you some of the work that I was doing. We can compare and contrast notes. I think we were working on it in parallel without knowledge of each other. So that's a funny story.
Okay, cool.
Thank you.
Thank you too.
Hi, Mark and Marcus. Nice presentation. I had a quick question on when you said when you're classifying, you're doing ranking there. So what kind of, how many attributes are you talking about? Are you doing some scoring? Are you putting some weightage to the attributes when you kind of do any of those things?
I didn't understand the full question. So it's based on
Sorry, when you classify, you said that you have a lot of attributes in the taxonomy.
Yes.
So the attributes, you said you rank them, correct? Do you also weight them and say that this is more important than the other kind of thing?
No, this we don't do. So basically, we rank the systems which we then classified. So we didn't rank the attributes by themselves.
Okay.
In the end, we kind of have a ranking of importance measured by the explained variance in the systems, which lead to the construction of this design guideline. So here one could say, but I would not necessarily say that some of these attributes are more important than the others, but like the combination of them in order to, if you want to design a system which, it's basically it's the variance in the data. So like if you want to differentiate yourself or have kind of a quick approach to differentiate yourself, you could say that these attributes are more important. But
in a way, you can say which design questions make the biggest difference early on when designing a new system, and these 4 questions would, from our analysis, make the biggest difference in how the system at the end will look like.
I see. Okay. Thank you.
okay.
Hey, thanks, guys. Great talk. Great presentation. I missed the beginning, so you might have covered this, but what was the data source, and how much of it was it handcrafted, or how much like transformations did you have to do?
Yes. So the data sources. So we, I don't know if the slides are seen. So the data. We identified the systems by the system identification process. Yeah. And then we classified them ourselves. So me as the first author, then checked by the 2 co-authors and some students. So we had like several rounds of like internal expertise. And then we checked them by the community. So we sent out these classifications to 85, basically we had 85 respondents, and they evaluated if they agreed with the classification or not. So it's like a second layer of validation. So this was the data source.
All right. Thanks very much. Thanks for calling in.
Welcome.